Here we're going to talk about what are called hypotheses and possible conclusions we can draw when hypothesis testing. So first of all, I just want to talk with you about what a hypothesis is, what do we mean by that, and there are some examples here in a table. So this first one, remember P stands for the population proportion. So this first statement right here is that the population proportion is less than 1% or 0.01. So that's a statement about it's a hypothesis. It's simply a statement about the population proportion. So a hypothesis is a claim or a statement about the value of a single population characteristic, in this case the population proportion. Here's another statement or hypothesis that the population proportion is less than 0.25. Next one is the population proportion is greater than 0.8, and these are gives you an explanation of the context of these, but I'm just reading these mathematically. So here the population proportion is greater than 0.8, and another hypothesis might look like this: the population proportion is equal to 0.3. So we're making these statements, these hypotheses, and they are statements about the population characteristics, okay? Not the sample statistics, but these are statements about the population, something about the population characteristic. So sometimes we have competing hypotheses, okay? So for example, you may have a situation where you have this. One statement says that the population proportion is less than or equal to 0.5, and this statement says that the same population characteristic is greater than 0.5. So the question is, well, we call these competing hypotheses, and the question is, which one of those is true? So the question, we're going to answer that question. How do we decide between two competing hypotheses? So this is the logic. We're moving into the logic of hypothesis testing. So a hypothesis test uses sample data to choose between two competing hypotheses about a population characteristic. So this is some terminology that we're going to use. The null hypothesis, denoted by H with a little sub-zero, so H naught, or we just say the null hypothesis when you see that little H sub-zero. And it's a claim about a population characteristic, and here's the important part for hypothesis testing: that it's initially assumed to be true. That's very important. Is that when we do hypothesis testing, we're assuming that the null hypothesis, whatever that statement is, we're assuming it's true. Okay? And then we have a competing hypothesis, which is called the alternative hypothesis, and it's noted with a capital H, but with a little sub a right there. Okay, so it's a competing hypothesis. So the way this is going to work is as follows, and I've written this as critically important to understand, and we're going to see some examples and flush this out, but here's the basic idea. So in choosing between the null and alternative hypotheses, you initially assume the null hypothesis is true. Okay, now this next sentence is critical. When you observe data that would be very unlikely to occur if the null hypothesis was true, you then have convincing evidence against the null hypothesis. Okay? In that case, the alternative hypothesis, you have convincing evidence for the alternative hypothesis. Okay, and then we'll talk about the other case in a moment. So basically the way we're going to see is the way everything sets up with hypothesis testing. You can only draw one of two conclusions. The first conclusion is this, is that you can reject the null hypothesis. That is, you can reject that initial statement about the population characteristic. Okay, that's called rejecting the null or rejecting the null hypothesis. The other option is that you can fail to reject the null hypothesis. So these are the only two options. Either you reject the initial one or you fail to reject the initial one. Notice that there's no confirming the null hypothesis. It's only either you reject it or you fail to reject it. And I'll talk more about what that means in a minute. So let me give you an example before we get too far into this here. Let's see, I froze up for a second there. Okay, so here's an example to think about this. Imagine we had two competing hypotheses about a population. Okay, so this is the null hypothesis, and I know it's the null hypothesis because of the little sub-zero right there. So the null hypothesis is simply that the population characteristic is 0.67. And then the alternative hypothesis, that is the competing hypothesis, is that the population characteristic is less than 0.67. So the question is, how will taking a sample and calculating the sample proportion and the sampling standard deviation, how will that help us decide between H naught and the null hypothesis and the alternative hypothesis? So imagine this. So remember, we're trying to decide which of these two we have evidence for. Let me be careful with that. You never have evidence to support the null. So the only options are either you reject the null and go with this, or you fail to reject the null. Now, if you fail to reject the null, that doesn't mean that it's true. It just means that you don't have evidence to reject it. Okay? So imagine these two scenarios. Imagine first that we got a sample and we calculated a sample proportion and it was 0.59. Okay. So remember, we're assuming 0.67 is true. So if you do that, that assumption of 0.67 being true, that leads to, let me show you this. I'm going to blow this up for you so you can see it. When you do that, when you assume 0.67 is true, what that does is that sets in some wheels in motion that give you a sampling distribution centered at the population characteristic, in this case 0.67. So when we did this, when we assumed the null was 0.67, then that gives us a sampling distribution, assuming the sample size is large enough, where the sampling distribution is normally distributed. Okay. Now I'm just assuming for this argument right now, that let's say that the standard deviation of the sampling distribution, let's say the standard deviation was 0.06. Now, if I'm imagining I'm in scenario 1 where the sample proportion I got was 0.59, here's what I've constructed. A sampling distribution that's centered at 0.67, and I'm asking myself, how likely is it that I get 0.59 or smaller for a sample proportion? That is, if I got my sample 1 and it was 0.59, the question I'm asking myself is, what are the odds of getting a sample proportion that small, so 0.59 or smaller, assuming the truth of 0.67? That's what this graph does for you. It gives you the probability, and the probability is the area of the orange region. Okay, it gives you the probability of getting a sample proportion of 0.59 or smaller, assuming the null hypothesis, that is, the underlying population proportion, was 0.67. So what is that probability? The probability of getting something 0.59 or smaller is 9%, 9.1%. Okay. So I say to myself, that's interesting. If this was true, the odds of me getting a sample like this, where the sample proportion is this or smaller, is 9%. That's a pretty high probability, right? So that doesn't give me intuitive reason to think this might be false. Why? Well, because when it's true, about 9% of the time, I'll get a sample proportion that's about that size, right? In other words, this was not so shockingly different from my assumption that it didn't lead me to draw the conclusion that, there's a very low probability of this occurring, so that's false, so I'm going to reject that. In other words, this occurs fairly frequently if the true population was 0.67, okay? But now imagine we had a different scenario. Imagine that instead of getting a sample proportion of 0.59, you got a sample proportion of 0.51. And the first instinct when I see that is like, wait a minute. I got a sample proportion of 0.51, but I'm trying to think about whether or not the underlying population was 0.67. Wow, those seem pretty far apart. So I'm going to draw the same graph that I drew over here, and it's still going to be centered at 0.67. But now, instead of asking myself, what's the probability of getting a sample proportion as extreme as 0.59, I'm going to say, what are the odds of getting a sample proportion as extreme as 0.51? And when I do that, when I look at the sampling distribution, again, it's centered at 0.67. That's established by the null hypothesis. The null hypothesis always establishes where the mean of the sampling distribution is, because this is an unbiased statistic. So when I look at that, right, when the null sets, okay, the null's at 0.67, the null tells me the population proportion is at 0.67, what are the odds of getting a sample proportion as extreme as 0.51? Whoa, a very small orange area. And what that means is that I look here and I see that the probability of getting a sample proportion as extreme as 0.51, that is 0.51 or smaller, is only 3.8%. In other words, I take that back. Not 3.8%, 0.3%, right? So the odds of getting this sample proportion, if that really was true, is only, I moved the decimal over 2 places, is only 0.38%. So that tells me that, whoa, that getting a sample proportion like this, 0.51, is very, very unlikely. So if we got it, which we did, right, because we got a sample of that, this says, imagine we got that sample proportion, that would make me think that I have good reason to think that the underlying population proportion was not 0.67, that it must have been smaller. Because look, the odds of getting this were so low, and yet we got it, right? Which means that, whoa, I'm not thinking that it was really centered here. I bet it was centered lower than 0.67. I bet the true population proportion was less than 0.67, okay? That's the logic of hypothesis testing, is you look at the rareness of the sample proportion you got with the assumption of the population proportion, and then you ask yourself, is the rarity of the sample you got enough to convince you that the underlying assumption of this, the truth of that, is that is not true? Does it give you reason to reject that? Okay, so let's go ahead and just flush this out a little bit. Now, I wanted to point out here that the distribution is always a combination of these two ideas. If H naught was true, because the H naught is true is always what centers your sampling distribution, what is the probability of getting a sample at least as unlikely as what we observed? That's the logic. So for sample 1, let's fill in the blanks. Let me choose about orange. So if this is for sample 1. If P was 0.67, and that doesn't change, right, because that's my assumption, I see from this graph the probability of getting a sample proportion of 0.59 or less is, what's that probability? It was 9.1%. So it's 9.1%. That is, the odds of me getting a sample proportion of this or less is 9.1%. This is not very unlikely because it occurs 9.1% of the time. That's not very unlikely. So we do not have a good reason to reject the null hypothesis. In other words, something this rare occurs so frequently that I don't have good reason to think that the underlying population proportion was different than 0.67. Right? I don't have good reason to reject the null hypothesis. On the other hand, for sample 2, if again the population proportion was 0.67, the probability of getting a sample proportion p hat of 0.51 or less, what was the probability of that? It was 0.38%. It was 0.38%. That's tiny. That's not even 0.5%. So the odds of getting this sample statistic, or this sample proportion, this is very unlikely. So we do have good reason to reject H naught. We do have good reason to reject the assumption that the population proportion was 0.67. And when we reject H naught, then that means we have evidence to draw the alternative hypothesis, the competing hypothesis, which is that the population proportion is less than 0.67. So another way, what I could have said for this as well, I could have said, we do have good reason to reject H naught, and then I could have added, and conclude the alternative hypothesis. Okay, because that's what happens when you reject the null hypothesis, is that you're saying you have evidence for the alternative hypothesis. Okay, so I wanted to point out that our book points out as well that a statistical hypothesis test can only demonstrate strong support for the alternative hypothesis, okay? You never, like in other words, think about this. I didn't reject the null hypothesis, but I didn't give evidence of I didn't reject this, but I didn't give evidence that it was true. And that's because all I can do here is say with a sample statistic how rare it was. And if it's very rare, then I think to myself, oh, then the underlying curve must not have been what I thought it was. That is, I reject this. But if I get something where that could have occurred, that doesn't necessarily mean this was true. It just means that I don't have reason to think it wasn't true. Okay? So that's what this is pointing out, is that you can only reject the null or fail to reject the null. And when you reject the null, you provide evidence for the alternative. But failing to reject the null doesn't mean you're giving evidence for the null, just means that you're not that just means that you're not rejecting that initial null assumption. So as we go down this road of hypothesis testing, it's very important that you construct the alternative hypothesis correctly. And the alternative hypothesis can only have one of three different forms. You can either have, for example, something like this: P is greater than, 0.3, let's say, or P is less than 0.3, or P is not equal to 0.3. You can only have an alternative hypothesis that has one of these forms. Notice that you can never have the alternative hypothesis containing the equality sign. And the reason is because the null hypothesis, and I'll address this a little bit later too, the null hypothesis always contains the equality sign, because when it does, that's what allows us to construct a sampling distribution centered at that population characteristic. Okay, so it's very important that your null statement always contains the equality sign, and your alternative statement never contains the equality sign. Okay, and that's what this is saying here. So as we saw in the previous example, the null hypothesis was that P is equal to 0.67, and the competing alternative hypothesis was that P was less than 0.67. So as a practice for this idea and to see how things are related, let's ask ourselves this question: what conclusions can we draw if we had this following situation? The null hypothesis was P is 0.75. The alternative hypothesis was P is greater than 0.75. And we observed a sample proportion P equals 0.89. Well, the logic is this. If the null hypothesis is 0.75, then you have a sampling distribution centered at 0.75. Now remember, see what the alternative hypothesis is saying is, it's that the population proportion is greater than 0.75. So now we want to know if there's evidence that the underlying population proportion is greater than this, not less than this like it was before, but greater than 0.75. Now, if your sample proportion is 0.89, you want to know what are the odds, and the reason is because of the direction of this inequality right here. When you have the arrow pointing to the right like that, that's saying that you want to know what are the odds of getting a sample statistic rare enough to give evidence that this is true. Okay, so my sample statistic is 0.89, and I ask myself, what are the odds of me getting a sample statistic that's greater than or equal to 0.89, assuming that the null hypothesis, or assuming that this is the underlying population characteristic? What are the odds of me getting a sample proportion greater than or equal to 0.89? And the odds are 3.8%. So in other words, if the underlying, let me go back up here, if the underlying population characteristic is 0.75, the odds of getting a sample proportion of 0.89 or higher is only 3.8%. That's pretty rare. In other words, I got a pretty rare value for a sample statistic or a sample proportion. And that makes me think my underlying assumption was not true. It makes me think this is true. that the underlying population proportion was greater than 0.75. So here's the conclusion I draw. If H naught is true, that is the underlying population proportion is 0.75, we see that getting a sample proportion as extreme as what we got, p hat equals 0.89, happens only 3.8% of the time, right? Which is pretty rare. The fact that we got such a sample proportion gives us reason to conclude that the underlying p, the underlying population proportion, was greater than 0.75. In other words, we reject the null and conclude the alternative hypothesis. In other words, getting this is so rare. If that was true, it makes me think this wasn't true, and that the underlying population proportion must have been greater than 0.75, okay? All right, now I want to give you, or let's have a little bit of practice choosing the correct form of the alternative hypothesis. So I have a few examples here. First example is, so there's a survey of a representative sample of 18 to 34-year-olds, and suppose that we're interested in determining if the sample data supports the claim that fewer than 1/3 of adults in this age group are living with their parents. So let me underline this. This is important. We are interested in determining if the sample data supports the claim that fewer than 1/3 of adults in this age group are living with their parents. So they tell us that with p equals the proportion of adults 18 to 34 who live with their parents, that's what p represents. So the question is p less than 0.3? 0.33. So the hypothesized value is 0.33, and the appropriate alternative hypothesis, because remember what I said earlier is that you're only in these, when you're hypothesis testing, your only ability is to have evidence that supports the alternative. So if you're asking yourself, do I have data to support a claim, then you better make sure that that claim is the alternative hypothesis. Okay, so let me say that again. If you're trying to support a claim with data, then you better make sure that claim is the alternative hypothesis, because only alternative hypotheses can be supported with data. So if the sample data, you want to know if the sample data supports that fewer than 1/3 of adults in this population live with parents. So the appropriate alternative hypothesis, so H sub A, is that P is less than 0.33. That because this is what we want to show. We want to know if there's data to show this, and you can only have evidence to support the alternative. So you better make the alternative what you're trying to have data for, a claim that you're trying to support. So another one here, let's say that you were asked, there was a survey that asked survey participants if they thought they were in better financial shape than they were a year ago. And we're going to let P be suppose that you want to determine if the survey data provides convincing evidence. You want to know if the survey data provides convincing evidence that the majority of adult Americans believe they are in better financial shape than 1 year ago. Okay, so do you see what the alternative hypothesis is going to be? You want to know if P is greater than 0.5, right? That's because this is what a claim you want to know if you have data to support. Whoops. Let's try another one. So the manufacturer of M&Ms claims that 40% of the M&Ms of plain M&Ms are brown, and a sample of M&Ms will be used to determine, okay, here's what the claim you're trying to determine. Determine if the population proportion of brown M&Ms is different than what the manufacturer claims. That's what you want to test. Okay, that if the population proportion is different than this, therefore your alternative hypothesis is that P is not equal to 0.4. That is different than 0.4. And then finally, last example, here you want to know if you have a study where data supports the theory that a majority of adults in Israel believe they are less affected, that they are much less affected by reality TV shows than other people. Okay, so in other words, you want to know if P is the population proportion of Israeli adults who believe they are much less affected than other people, and you want to test if P is greater than 0.5. So that's your alternative hypothesis. So constructing your alternative hypothesis is super important because obviously that's the only claim that you can have data to support. Okay, finally, I wanted to point out something we mentioned earlier, which is that the null hypothesis has to be the population characteristic is equal to something. In other words, it's very important that you have the equality sign in there because that's what allows you to connect probability from the sampling distribution to what we're doing. And then finally, one last thing is that a statistical hypothesis test is only capable of demonstrating strong support for the alternative hypothesis by rejecting the null. When you fail to reject the null, it doesn't mean that you're supporting the null. That is, let me read that again. When the null hypothesis is not rejected, it does not mean strong support for the null, only lack of strong evidence against it. Okay. All right, so we're going to flush this out with more sections as we do some examples on hypothesis testing.